So the next application that we want to look at is arc length. So this is an attempt to answer this question. How long is a curve, right? Now the issue is we know how to measure distance, but we really only know how to measure distance along straight lines, right? So we know that if we have, say, a point here and a point there, right? And we know the coordinates for these 2 points. So if this is, say, x1, y1, and over here is a point x2, y2. Well, we know how to measure the distance between them, right? We just draw the line from there to there. And then we rely on essentially Pythagorean theorem, right? We set up this triangle. We know that delta x is just x2 minus x1. We know that delta y is y2 minus y1. And if we have this distance d, well, Pythagoras says that the distance squared is delta x squared plus delta y squared, okay? So this is something we understand and we know how this works. Another question is, well, what if you go from there to a situation where you're going between 2 points, but you're not doing it in a straight line, right? So what if you're going from here to there, and instead of following a straight line, you follow some curve? Maybe we travel like this. How do we measure the distance now? Well, we fall back to a technique that we've done many times in the past, right? We still start with an initial point x1, right? So this will be, maybe we call this A. We're going to end at some final point B. And we're going to call that maybe x n plus 1, and we're going to introduce a whole bunch of other points in between, right? x2, x3, x4, and so on, right? We partition. And so that partition, well, it introduces a bunch of intermediate points on our curve. Like so. Right? So it's a very similar picture to the one that we encounter when we're doing, let's say, areas or something like that, right? We partition, but this time we're not going to try to calculate the area of rectangles or do anything like that. Instead, what we're going to do is we're going to calculate the distance between points, right? And for portions of the curve where the concavity is small, as measured by the second derivative, this works pretty well, right? The deviation from a straight line here is not that significant. Same thing here, right? So let's try this in maybe white will work better. There, there. There we see a bit of deviation, and there. There it's more significant. There it's more significant. And there, right? But this sort of piecewise linear path, it's a reasonable approximation to the original path. And as you take more and more points, the approximation gets better and better, right? And so this distance that we're this length of the curve, right? The length that we're interested in, well, it's approximately, that first distance squared plus the second distance squared, right, down to the last distance squared, where each of these distances, well, we can say exactly what it is, right? Di is going to be the square root of delta xi squared plus delta yi squared, right? And probably you want to do a uniform partition. That's sort of standard practice for us, right? So if we're doing a uniform partition, Then we know that delta xi should just be delta x, our usual b minus a over n for each I going from 1 up to n. Okay. What about delta yi? Well, delta yi is going to be f at xi plus, oops, sorry, should be in the subscript, I plus 1, right, minus f at xi, okay, for each I. Okay, so we can kind of put that together. We can sort of put this as a Riemann sum, but actually there's a thing we can do which is even better. By the mean value theorem, I can take this difference and I can write it as, and now of course now I have to assume that my function is differentiable, continuous, right? So, and of course if it's at least continuous, right, maybe there's some points where it's not differentiable. But those are typically going to be cusps, corners, things like that. And we can still calculate the length by breaking, the curve up, right? If it's continuous but it's not differentiable, it's probably at least piecewise differentiable. I mean, probably. I mean, you can construct curves that are continuous everywhere but differentiable nowhere, really bizarre objects you might encounter in like an analysis course later in your life. But for the sort of things you encounter in calculus, typically worst case scenario is it's piecewise differentiable and you can apply this picture to each part. So if we assume differentiability, then the mean value theorem guarantees that we can write this difference as f prime at some ci times, well, the difference between xi plus 1 and xi, but that's just delta x, right? So we get delta x. And so ci here, well, ci is some number between xi and xi plus 1, all right? Okay, but coming back to this, what do I get now if I do delta xi squared plus delta yi squared? What do I get? Well, this is just delta x squared. The delta yi squared becomes f prime of ci squared, and also, again, delta x squared. Well, you can factor out that delta x squared, right? 1 plus f prime of ci squared. Okay? And so now you want to move from the approximate to the precise using limiting arguments the way we usually do in calculus. And so we say, okay, well, look, that means that what this distance is going to be here is going to be 1 plus f prime of ci squared, all under the square root. Square root of delta x squared is just delta x. So we sum all of these. That gives us something that looks an awful lot like a Riemann sum, right? It is essentially a Riemann sum. And we take the limit as the number of partition points goes to infinity, and we get an integral. We get an integral that looks like the integral from a to b, 1 plus f prime of x squared times dx, right? That's going to let us calculate the length of the curve. So now that we've got our formula, we'll put it to use in a number of examples.